Hello there. This is a video lecture that goes along with the nature of statistics. Um, in this video, we're going to look at what is statistics, what's the definition of it, what are the main pieces for it, and what are some key terms to it. So we're going to briefly get into that. There's not a lot of mathematics in this section, mostly text, qualitative stuff that we need to learn to set the foundation for this course here. But in statistics, what's going on is we observe something about the real world. Okay, so we have something about the real world, then we must infer the details about the phenomenon which produced what we observed. This idea of infer is important. Basically, it has the connotation that we are drawing conclusions based on partial information, and that's a common thing within statistics, the field of statistics. A problem, though, that can arise is, and it happens often, that more than one phenomenon, more than one structure can give rise to the observations in hand. What you've got may be the result of something that you can't foresee, but that you would like to be able to foresee. Here's an example. So a common problem for a married couple is the difficulty in conceiving a child. And so in part of this bigger problem, a sub-study might be to look at a particular toxin in a workplace that might have an effect on women becoming pregnant. So it is thought that women exposed to a particular toxin in the workplace could have greater difficulty in becoming pregnant compared to those who are not exposed to the toxin. And so what could be done is you conduct a study of such women, recording the time it takes to conceive. Okay. Now, when you think about time to pregnancy, there's of course natural variation. That has causes aside from the toxin, the age of the female, the male himself, other factors attribute to the time to pregnancy, and so there's natural variation in that time. But we want to see basically is there greater time as a result of or greater difficulty in becoming pregnant as a result of exposure to this toxin. Okay, but what if there's another variable you did not consider that could be a cause? Maybe what if there's something else there? No study can pick up every possibility. For example, it turns out that women who smoke while they are pregnant reduce the chance that their daughters will be able to conceive because the toxins involved in smoking affect the eggs in the female fetus. So if you were to conduct a different study later down the road, seeing if, okay, this female that was eventually born is now wanting to conceive, if you don't have this information, if her mother was a smoker or not while she was pregnant, then you might draw some wrong conclusions about this particular toxin. And so being aware of this sort of thing is important. So this just kind of gives you a sense of some things that we run into in statistics. Setting up a study is important. Knowing what you're going to observe is important. But in particular, what we want to do in statistics is we want to draw conclusions from the data. And these are inferences that we make. And when we do that, they always come with some amount of uncertainty. And we want to quantify our uncertainty so that we can know how good our conclusions are. Now, scientists use statistical inference to help model the uncertainty inherent in their investigations. In this course, we'll introduce you to such statistical methods. What is statistics? Is statistics simply the study of baseball players' batting averages? Is it the study of salaries for a particular demographic group in a particular state at a particular time? Is it more than just looking at numbers, computing percentages and averages and this sort of thing? Turns out it is, and your book has a nice definition for it. Your book says that statistics is the science of learning from the data. And that there's 4 steps associated with this learning from the data. The first step is you actually want to design the problem. If you're going to go out and gather data, you need to know how you're going to gather it, and you need to set up the problem, set up the design structure appropriately, and that's step 1. In learning from the data. Step 2 is collecting the data. Step 3 is summarizing the data. Step 4 is, now that we have all this data and we've summarized it, we want to analyze the data, we want to interpret the data, and we want to be able to, well, I say interpret the data, interpret the analyses that we're going to use here. And then also we want to be able to communicate the results. Let's see, I've kind of, my window has shifted over. Let me see if I can fix that. Uh-oh. Okay. All right. Here is a table from your book, table 1.1, from the 6th edition of Ott and Longenecker, that organizes the text within the four-step process of learning from the data. Step 1, introduction, and that's kind of what we're looking at here, is covered mostly in chapter 1. Step 2, collecting the data. How do you collect the data? All right. Step 2, collecting the data. We're going to look at some survey methods and experimental studies to gather the data. That's from chapter 2. Step 3, summarizing the data, deals largely with chapters 3 and 4. And then if you look here at step 4, analyzing, interpreting, and communicating, those consist mainly of chapters 5 through 19 and make up the bulk of this textbook, but also the bulk of what we're going to do in this course. We're going to, a common starting place for us is we're going to assume we have some data and we want to summarize it and then analyze and interpret the data as well as communicate it. Now we won't get through all 19 chapters in this course, but we'll get through a good bulk of those sections that deal with step 4 there. Well, that is the book's definition. What is statistics? It has this nice 4-step procedure to it: design the problem, collect the data, summarize the data, analyze, interpret, and communicate. I like this other definition as well. I want to make you aware of it. The art of collecting, organizing, summarizing, and describing data, as well as drawing inferences from the data. Okay, that's the field of statistics. And it's often broken up into 2 sections: descriptive statistics and inferential statistics. Now, descriptive statistics deals with, hey, you've got data, you want to organize it and you want to summarize it in a meaningful way. And that's going to be largely chapter 3 for us. Inferential statistics deals with drawing conclusions about a population based on a sample, and then also measuring the reliability of those conclusions that you draw about that population. That deals with inferential statistics. Sometimes we'll say inferential statistics is a branch of statistics that deals with this process. Sometimes we'll use the phrase statistical inference, but we mean basically the same sort of thing. Now, within really descriptive statistics and inferential statistics, there's several important terms here that we want to look at. First, this idea of a variable. And a variable is simply a characteristic that takes on potentially different values for different people, places, or things. So for example, the time it takes a person to walk from point A to point B, the amount of gasoline a person puts in their vehicle, the color of a person's dog. Those are all variables. They're potentially different from different people, places, or things there. Now we look at two kinds of variables. One is called a quantitative variable, and the other is a qualitative variable. Quantitative is a variable that can be measured numerically. Qualitative is a non-numerical characteristic that can only be put into categories. Okay, so the time it takes a person to walk from point A to point B, that would be quantitative, an example of a quantitative variable. An example of a qualitative variable would be, a person's hair color or eye color or gender, this sort of thing. Now, when we have a variable and its result, it's obtained as a result of a chance factor, then we call that a random variable. And in particular, we can think of a random variable is a variable if the exact value of the variable cannot be predicted in advance. Two kinds of random variables that we have are a discrete random variable and a continuous random variable. A discrete random variable is one when the variable can only assume a countable number of values. And this is so that word countable, it has a particular mathematical meaning, that there's a relationship between the positive integers and every possible value of this random variable. That can be an infinite amount, but typically a discrete variable has usually a finite number of possible values. So for example, tossing a die, there's six possibilities there. Okay, the number of siblings a student has, that's something that you can count: 0, 1, 2, 3, and so forth. That's a discrete random variable. A continuous random variable is when the variable can theoretically assume an uncountable number of values on a given interval of the real number line. Okay, and so some examples of this are things like the time it takes to walk from point A to point B, or the amount of gas that a person puts in their vehicle. Time and volume, length, those sorts of things are values that mathematically can be given any real number, and so we think of that as a continuous random variable. Throughout the text, we'll deal mainly with continuous random variables, but discrete random variables will have an important role as well. So we have these variables and random variables. Some more important terms for us is this idea of a population. Now, the population is the collection of all individuals or items under consideration in a statistical study. So if we think back to the study above, dealing with couples wanting to conceive, that would be the population. You know, women that are at childbearing age, that are desiring to conceive. We would be interested in studying that population. Now, typically, the researcher cannot look at the entire population. And so the researcher must take a subset of the population, which is called a sample. So the researcher looks at a subset of the population and wants to use that somehow to say something about the population. But strictly speaking, a sample is a subset of the population, okay? Representative sample is when the characteristics of the sample represent the characteristics of the population. And you want this to occur. You want your, what's often said, your target population to be the same as your sampled population. If that's not the case, then any inferences you draw based on your sample can have some real problems to it. Next term here is a parameter. Parameter is a numerical description. A numerical description of the population. Because a parameter is a numerical description of the population, it tends to be unknown because the population, we don't have the entire population in front of us. A statistic is a numerical description of the sample. All right, and so that is known because we do know our sample, and typically what's done is we use our statistic to somehow estimate our parameter, and that gives rise to this last term here, inferential statistics, sometimes called statistical inference in terms of a process. But the field of inferential statistics is using sample information to draw conclusions about a particular population, and this is usually done in the sense that we use a statistic to say something about the parameter. Okay, now here's a picture. Here's a picture that's useful in understanding the field. Let's see here. Kind of lost my, sorry about that. I'm still kind of getting used to this program. Here's a picture that helps us think about the field of inferential statistics. We have this population that we want to say something about, all right? And so you have a population here, and its reality. So maybe we want to say something about childbearing women, or women of childbearing age that desire to get pregnant. We want to say something about them. Okay, we can't look at that entire population, so what we do is we take a sample, and we have a sample here, and we can let the sample be represented by a particular value of a variable x1, x2, x3 up to xn. And from our sample we can compute certain things, and we'll talk about this later on in the course, but we can compute things like a sample mean and a sample standard deviation. We can compute a sample median. Those are things I'm sure you've heard of before. We can also get a histogram, which is just a picture of the data in some sense. Again, we'll talk about that later on, but we describe the data, and once you have the data and you try to use that data to say something about this population model. That's a chapter 4 idea that we'll get to. And really this population model is a mathematical idea, and it's almost part of an imagination. You hope that it describes the reality of the population. There's ways to check that, but we use our sample to say something about our population model. In particular, we want to say something about parameters within that model. Okay, but this is a nice picture. I suspect I'll come back to this in later lectures, as it gives you a good sense of what statistical inference is. Taking a sample from a population, using the statistics from that population to say something about the population model or parameters that help describe that population. That is the field of, or the nature of, statistics.